Hello everyone, here we'll be discussing chapter 8.5, which is a discussion on the complex plane. Now the complex plane is, I guess you can say, analogous to the real number line. In fact, it's kind of an extension of the real number line. So recall first that the imaginary unit I is a number such that I squared is -1, and this is not a real number. No real number squared will result in a negative ever. So beyond this, we can say that a plus bi is a number, quote unquote number, where a and b are real numbers. So recall this notation here. This symbol is in. So you can say this, the a and b are in, so they're each in. R, which should have a double slash through it like this. Now R with a double slash through it like this is the set of real numbers. So that R stands for the set of real numbers. And this number a plus bi, where a and b are real numbers and I is the imaginary unit, is known as a complex number. Now the set of all complex numbers is C. So R is the set of all real numbers, like this, and C is the set of all complex numbers. So like I was saying, the real numbers lie on a number line. So kind of think of a number line like this. And usually we'll denote it by R, just to denote the real number line. And very often you'll see it with a 0 in the middle, positive numbers on the right, of course, and negative numbers on the left. In fact, we'll kind of be rewriting this here. Now with the complex plane, we're going to define an x-axis and a y-axis. The x-axis will actually be a real number line. And the y-axis will be the so-called imaginary number line. Now an imaginary number is just a number times I, a real number times I. So in reality, this is just I multiplied by each real number. So we kind of get this twice. We get this horizontally, and then vertically we'll get each of those numbers multiplied by I. So here we have 1, 2, 3, for instance, and here we'll have I, 2i, 3i, and then down here we'll have the negative ones. So let me just write negative I, negative 2i, negative 3i, if that makes sense. And how we plot a complex number is we actually consider the number a plus bi to correspond to the point a comma b, where of course b is really just the y value here, bi. So we're kind of thinking this as a point. We're thinking of this, this number as a point on the plane, which makes sense if you think about it, because any real number can be thought of as a number on the line, a point on a line. So a real number, if you think of any real number, like for instance the number 2, pi, 3, square root of 5, any of these real numbers, these are all really good examples of real numbers. They all lie somewhere on the line. I does not, though, because there's no number that when you square it will result in -1. That's a real number. So for that reason, anything that's of the form a plus bi must be a point on the complex plane. So basically we think of these numbers as one-dimensional because they lie on the one-dimensional line, whereas we think of a complex number as two-dimensional because there's two components to it, a and b. So for instance, if this point is a and this point is bi, then the point a comma bi, so maybe I should write comma bi like this, represents the number a plus bi. So it's a point on the plane. And very often we relate this to vectors. So this is kind of the reason why we were talking so much about vectors in 8.3 and 8.4, because we can relate these to complex numbers, and we've seen complex numbers before, in a little bit anyways, in Algebra 1. So now this is kind of a callback to that and relating that to vectors, which we can now incorporate trigonometry into. We'll do more of that in 8.6. But now I wanted to find an absolute value. Now, what does absolute value for real numbers mean? Well, we often think of absolute value as just removing the negative, but it really means the distance from 0. So consider -2 and +2. They both have the same absolute value, which is 2. So we can say that the absolute value of 2 and the absolute value of -2 is the distance from those numbers to 0. That's one way you can define absolute value. And we can do that the same way here. So, in other words, if we were to create a line between the origin and a point a plus bi, notice what we end up getting actually is a right triangle whose vertical length is b and whose horizontal length is a. Now, of course, you can think of this as bi, but we're looking at the distance. So the amount of units we travel here would be, I guess, bi, but since I is considered a unit, there's really b spaces we travel. Think of it like that. So with that being said, the distance here would be what? This distance would actually be the absolute value of a plus bi. Perfect. And we can find that using Pythagorean theorem. Really, it's just the square root of the sum of the squares of the components. This should remind you very much of magnitude with vectors. Basically the same thing, actually. So I haven't given us any space here for examples. Maybe I could just throw in one example here for absolute values. So let's consider the absolute value of negative 3 minus 4i. That's not too bad of an example. So negative 3 comma negative 4i, of course, is in the third quadrant here. Its x value is negative 3, its y value is negative 4i. So it's somewhere down here. And the distance from the origin is just going to be the square root of the sum of the squares of its components. Now the components actually have names. So when I say components, I'm not talking about a and bi, I'm just talking about a and b. So just the real number components. Now, they have names. A is usually referred to as the real part, and B is referred to as the imaginary part. So it's important to know that the imaginary part is not bi, but it's b itself. So it's the numbers multiplied to I and the number that's added to that. So the real part is A and the imaginary part is B. Great. So with that being said, if we square those parts, and then add those results together, we get the square root of 9 plus 16, which is of course 25, and then the square root of 25 is 5. Awesome. And what you'll notice is that we'll actually always get a positive value here, and it makes sense because since we have a square root involved, and the inside of the square root is always going to be real because we're not considering actually plugging an I into anything here, we're only considering A and B themselves, will result in the square root of a real number, which will be positive, because there's no negative outside of the radical. We're only considering the positive root because we want to consider this as a positive distance. So that makes sense. And in fact, really, any real number, this part's a little funny, but any real number is actually in its own right a complex number. Because you can take your favorite real number, like let's say pi, and you can actually write pi as pi plus 0i. So the number pi is on the complex plane, it's about right here. It's a little bit to the right of 3, right, 3.14159 something, and its y component, or I guess real part, is 0, so it's completely on the real number line. Much like we would have plotted here, but now we see it in the complex plane. Since the real number lies in the complex plane, every real number in its own right is a complex number. And with that being said, if we wanted to take the absolute value of pi, we can use this definition here, and we'll still get the same result we would get otherwise. In fact, you can kind of see, if b is 0, when you square a, no matter if a was negative or positive, you'll result in a positive square, and then square rooting that will give you the positive version of that number. So if you wanted to find the absolute value of negative 5, doing this, when b is 0, of course, because negative 5 has real part negative 5 and imaginary part 0, it will result in absolute value 5. So you'll still get the same thing. So this is a good extension of our notion of absolute value. So I think I've spoken enough here. Now I'm going to do some examples regarding some other properties of the complex plane. All right, so the next and basically last things I want to talk about are addition and subtraction and conjugates. And I'm of course going to relate to what actually happens in the complex plane, but to add or subtract two complex numbers, we basically just combine like terms, and essentially what it is adding component-wise. Similarly for subtraction, it would be a minus c and b minus d. So you can kind of see that if you combine a and c, you get a plus or minus c, depending what operation you have, of course. And for the bi and di's, you get bi plus or minus b di, but then since they both have I in common, you can factor that out, and you get b plus or minus d times I. And again, either it's all subtraction or all addition. So, right. So now I'm going to do one example of each, and I'm going to plot them in the complex plane so we can see what happens. And spoiler alert, it's basically just addition and subtraction with vectors. So we'll kind of see what happens here. So if we add these, so adding 3 to negative 3 and then adding 2 to negative 5 will give us what? Well, 3 minus 3 is going to be 0, plus 2 minus 5 is actually negative 3i. So this amounts to negative 3i. So that's our answer here. But I'll actually plot this along with the originals to kind of see what's going on in the complex plane. Right. So in the complex plane, we have the point 3 plus 2i, which is right here, and negative 3 minus 5i. Negative 3 minus 5i would be over here. That's negative 3 minus 5i is down here. Perfect. So now, the result when adding these is actually negative 3i itself. So negative 3i, let me write that in red, or I guess plot that in red I should say, is here. 3 units down on the imaginary axis, if you will. So now what's really happening is that if you take this vector here and this vector here, if we were to, so remember how adding vectors works. If we were to float this vector over here like this, keeping the same direction and same magnitude, it lands exactly on the red dot. So that's how you add vectors. You go from the tail point of one all the way to the head point of the other if you connect them head to tail, and then where you end up landing on will be the sum of those, which corresponds to this vector here, which of course we only want the point, which is negative 3i. So it's kind of nice we see that visualization. I'll try to show that again with this one as well. Right. So here we want to subtract, but the way we subtract is kind of like addition anyways, because you can distribute the negative and then combine. But let's just see this again as first minus the second, like this, for each of them. Now we have to be a little careful because we have numbers in front of I, but that's okay. We'll just kind of see what happens. So 2 minus 4 is negative 2. That's fine. And the negative I minus I, because we're distributing the negative, of course, is actually negative 2i. So that's not too bad. Notice the numbers in front are negative 1 and negative 1 after distributing the negative, so we indeed get negative 2i. Fantastic. So this is the answer here. And now I'll plot these 2 points and then plot this point so we can visualize the subtraction of vectors. So let's see if we can do that here. I think we'll be okay. So let's see, 4 plus I is going to be over here. Perfect. And 2 minus I is going to be down here at the real part 2 and imaginary part negative 1. Fantastic. Now the result was negative 2 minus I. The negative 2 is over here, and a minus 2i I should say, so that's going to be down here. Let me kind of move our tick marks a little bit. Okay. So the result in red, much like we had before, is over here now. So how can we explain this phenomenon? Well, we have this vector and this vector, and we want to subtract. So to subtract, basically what we're doing is we want one of these to be the resulting diagonal of the other. So in fact, you can kind of see that if you move this vector on top, which corresponds to 4 plus I, and if you float it over here, going from the red to this black one here, we indeed get that. Meaning that if we were to add the red vector, let me draw it in red, I guess, which is our result, to one of the black vectors, we get the other black vector. So, of course, this makes sense because this is just addition in reverse. So one of the pieces of the addition ends up being the subtraction of those 2 vectors there. So it's nice that we can see that visually, that these indeed basically correspond to vector addition and subtraction in the complex plane, which is nice. Great. Now we get into conjugates, and we say the complex conjugate of a complex number a plus bi is a minus bi, and the notation for complex conjugate is a bar on top. Okay, so now the complex conjugate of 3 minus 2i would then have to be 3 minus negative 2i, which is plus 2i. So basically we just change the sign of the middle number, of the middle sign, I should say. It's kind of more than that because you have to make sure it's in the specific order first, and we'll see that creep up with this next example. And I also want to plot these so we can kind of see what's happening with a complex conjugate of a number. So 3 minus 2i first is going to be down here. And 3 plus 2i will be up here. So we can kind of see that the vectors are just kind of reflective about the real axis. Which makes sense because since they have the same real part and their imaginary parts are negative, they're just literally reflections about the real axis. So that makes sense, and that'll actually happen here as well. But if we change the middle sign to I plus 2, that will not be the case. Now the reason why this situation happens again is because this is actually not in the form we want. The form we want is a plus bi, not bi plus a. So in other words, we have to first write this as negative 2 plus I. So it's technically in that form first. Now we can talk turkey with the conjugate, so to speak. So now we get a negative 2 minus I. Great. So again, that's changing the middle sign, but really when it's in order. So in reality, we're just changing the sign of the imaginary part. The real part stays the same. So this is my answer for this first example. This is my answer for the second example. And to plot things for the second example for complex conjugates, I minus 2 is the same as negative 2 plus I, which is over here in the complex plane without marking the tick marks. And negative 2 minus I would then be reflected about the x-axis or real part, or real axis I should say, because it's a negative 2 minus I now. Awesome. So we indeed see that they're reflected about the real axis. Now that's kind of all I want to say, but I will say this, just kind of an honorable mention, if you will. The book goes on to discuss the distance between 2 points in the complex plane and the midpoint between those as well. And those distance and midpoint formulas that we end up getting are the exact same that you would get in just the xy plane. So I'll let you look at that if you want, but I don't think it's worth it to go over because it doesn't really lead anywhere. It's a little... I mean, it's there, but you know, it's not something that will blossom into something beautiful, whereas these topics will. Of course, there's something that you may want to look at every now and then, but if you already have the idea of what distance and midpoints are, then we're okay there, but I don't want to give you a topic that'll just kind of have a dead end. These ideas are what we really need to discuss 8.6, and 8.6 will be the grand finale for chapter 8, where we can kind of finally see the relationship between trigonometry and complex numbers. It's going to be a lot of fun. I hope you enjoyed this. I know it's kind of a short video, but we saw a lot of really good stuff here. And the fact that we went over a lot of, in regards to vectors from 8.3 and 8.4, then we were able to kind of understand what's happening here and compare the complex plane to vectors, basically. So again, hope you enjoyed this. I'll see you in the video for 8.6. And thanks for watching. See you then.